Hi everyone, this is Alina from Chem 112, and today we're going to be talking about the solubility of various gases in water and their real-life applications. Before we jump in, we're going to look at a quick definition of solubility. So solubility is the ability of a solid, liquid, or gaseous chemical substance, commonly referred to as the solute, to dissolve in a solvent, which is usually a liquid. The solubility of a substance fundamentally depends on the solvent used, as well as temperature and pressure. The solubility of a substance in a particular solvent is measured by the concentration of the saturated solution. A solution is considered saturated when adding additional solute no longer increases the concentration of the solution. Also, it is important to note that solubility does not depend on particle size. Given enough time, even large particles will eventually dissolve. So, the chemical structures of the solute and solvent dictate the types of forces possible, and as a result, are important factors in determining solubility. For example, under similar conditions, the water solubility of oxygen is approximately 3 times greater than that of helium, but 100 times less than the solubility of chloromethane. We're also going to be looking at other factors that affect the solubility of a given substance in a given solvent in just a minute. Temperature is one such factor, with the gas solubility typically decreasing as temperature increases. You can see this relationship in the graph below with all the noble gases. This is actually one of the major impacts resulting from the thermal pollution of natural bodies of water. When the temperature of a river, lake, or stream is raised abnormally high, usually due to the discharge of hot water from some industrial process, the solubility of oxygen in the water is decreased. Decreased levels of dissolved oxygen may have serious consequences for the health of the water's ecosystems and, in severe cases, can actually result in large-scale fish kills. The solubility of a gaseous solute is also affected by the partial pressure of solute in the gas to which the solution is exposed. Gas solubility increases as the pressure of the gas also increases, so there's a direct relationship. Carbonated beverages provide an illustration of this relationship. A real-life example is the carbonation process, which involves the exposing of a beverage to a relatively high pressure of carbon dioxide gas and then sealing the beverage container, thus saturating the beverage with CO2 at this pressure. When the beverage container is opened, a familiar hissing noise is heard as the carbon dioxide gas pressure is released, and some of the dissolved carbon dioxide is typically seen leaving solution in the form of small bubbles. At this point, the beverage is supersaturated with carbon dioxide, and with time, the dissolved carbon dioxide concentration will decrease to its equilibrium value, and thus, the beverage will become flat. You can see this process illustrated in the equation below between water and carbon dioxide, which forms carbonic acid. So now we're going to look at a quick example using Henry's law. This law states that the quantity of an ideal gas that dissolves in a definite volume of liquid is directly proportional to the pressure of the gas. And you can see this relationship here to the right. Cg equals Kpg, where Cg is the solubility, K is the proportionality constant, and Pg is the partial pressure. Looking at the example down below, at 20 degrees Celsius, the concentration of dissolved oxygen in water exposed to gaseous oxygen at a partial pressure of 101.3 kilopascals, or 760 torr, is 1.38 times 10 to the negative 3 moles per liter. Using Henry's law, determine the solubility of oxygen when its partial pressure is 20.7 kilopascals, or 155 torr, which is the approximate pressure of oxygen in Earth's atmosphere. Because we know both Cg and Pg, we can rearrange this expression to solve for K. So now you can just plug in the numbers. For Cg, you have 1.38 times 10 to the negative 3 moles per liter. For Pg, or partial pressure, you have 101.3 kilopascals. And if you calculate that, you can get 1.38 times 10 to the negative 5 moles per liter divided by kilopascals. And you can also get 1.82 times 10 to the negative 6 moles per liter per torr. And then you can use K, which you already found, to find solubility at a lower pressure. So to do this, you just multiply your answer of K times the partial pressure, which is 20.7 kilopascals, and you're going to get 2.82 times 10 to the negative 4 moles per liter. So therefore, the solubility of oxygen gas at 20.7 kilopascals is 2.82 times 10 to the negative 4 moles per liter. And note that any combination of units that yield to the constraints of dimensional analysis are acceptable for this calculation. Looking at the solubility of ammonia in water, you can see the same relationship here, where as the temperature increases, the solubility decreases. So ammonia is a colorless and pungent gaseous compound that is highly water-soluble and biologically active. Deviations from Henry's law are observed when a chemical reaction takes place between the gaseous solute and the solvent. So for example, the solubility of ammonia in water does not increase as rapidly with increasing pressure as predicted by the law, because ammonia, being a base, reacts to some extent with water to form ammonium ions and hydroxide ions. Now for the applications of ammonia in water. Ammonia is a biologically active compound found in most waters as a normal biological degradation product of nitrogenous organic matter, or protein. It also may enter ground and surface waters through discharge of industrial wastes containing ammonia and fertilizers. Ammonia has actually also been used in municipal treatment systems for over 70 years to prolong the effectiveness of disinfection chlorine added to drinking water. The addition of ammonia enhances the formation of chloramines, and it reduces the formation of carcinogenic chlorination byproducts. Finally, we're going to look at an interesting case study called decompression sickness. So decompression sickness, or DCS, is an effect of the increased pressure of the air inhaled by scuba divers when swimming underwater at considerable depths. In addition to the pressure exerted by the atmosphere, divers are actually subjected to additional pressure due to the water above them, experiencing an increase of approximately 1 atm for each 10 meters of depth. Therefore, the air inhaled by a diver while submerged contains gases at the corresponding higher ambient pressure, and the concentrations of the gases dissolved in the diver's blood are proportionally higher per Henry's law. As the diver ascends to the surface of the water, the ambient pressure decreases and the dissolved gases become less soluble. Actually, if the ascent is too rapid, the gases escaping from the diver's blood may form gas bubbles or embolisms that can cause a variety of symptoms ranging from rashes and joint pain to paralysis and even death. To avoid DCS, divers must ascend from depths at relatively low speeds of 10 or 20 meters per minute. Otherwise, they can make several decompression stops, pausing for several minutes at given depths during the ascent. When these preventative measures are unsuccessful, divers with DCS are often provided hyperbaric oxygen therapy and pressurized vessels called decompression or recompression chambers. So thank you for listening. I hope you learned something new about the solubility of gases and Henry's law today.